Circularly polarized light. An electromagnetic wave is specified by the following electric and magnetic fields. E as a function of z and t is E amplitude cosine kz minus omega t I hat plus sine kz minus omega t j hat. Magnetic field B as a function of z and t is amplitude B minus sine kz minus omega t I hat plus cosine kz minus omega t j hat, where E and B are constant. Part A, what is the value of the line integral closed path integral E dot dl over the rectangular loop P shown in figure, which extends a distance h in the x direction and half a wavelength in the z direction and passes through the origin? Okay, so this is the figure. You can see x extends from 0 to h, z extends from 0 to lambda over 2, and we are on the y is equal to 0 point here, so on the y-axis. So this is on the xz plane. So we want to find E dot dl path integral for this rectangular loop. Okay, so you can see that this rectangular loop consists of 4 portions. Portion 1, where x goes from 0 to h. Portion 2, where z goes from 0 to lambda over 2. Portion 3, where z is equal to lambda over 2, x goes from h to 0. And portion 4, we have z going from lambda over 2 to 0, x is equal to 0. So let's specify these line elements along these paths. So for the first path here, dl1 vector, we are moving on the x-axis from 0 to h. So dl1 vector is dx I hat. Along this path, z is equal to 0, y is equal to 0, x goes from 0 to h. All right, so that's the first portion. The second portion, x is equal to h, z is changing from 0 to lambda over 2. We're moving along the z-axis. So for this part, I have dl2 vector is dz k hat. Z changes between 0 and lambda over 2. Y is equal to 0, x is equal to h. So for the third portion, I have this part, z is equal to lambda over 2, x goes from h to 0. So dl3, I have dx I hat, where z is equal to lambda over 2, y is equal to 0, x goes from h to 0. All right. And for the fourth one, that is this last one here, z goes from lambda over 2 to 0, but x is equal to 0. So let's talk about the fourth path. dl4 is equal to dz k hat. Z goes from lambda over 2 to lambda over 2 to 0. Y is equal to 0. X is equal to 0. And now if I write the electric field vector, electric field as a function of z and t is given as the amplitude E cosine kz minus omega t I hat plus sine kz minus omega t j hat. So when I take the dot product of the electric field vector with these line elements, I will encounter I hat dot and j hat dot products. So whenever I have I hat dot k hat or j hat dot k hat, the answer will be 0. So I note that here I hat dot k hat is 0, and also j hat dot k hat is 0. So if I look at these line elements here, I have k hat on portion 2 and portion 4, which means that when I take the dot product between the electric field and these paths, there will be no contribution. So I conclude that there is no contribution from the segments 2 and 4. There will be no contribution from these segments because of this dot product being 0. Okay, so let's start writing the closed path integral E dot dl. So for the first path here, I'm going to take the dot product of this with dx I hat. So I hat dot j hat is 0, so this will give no contribution. This will be I hat dot I hat, which is 1. So I will have E cosine kz minus omega t dx, but z is equal to 0 on this path, so this is cosine of minus omega t. Cosine is an even function, so this is cosine omega t. So E cosine omega t dx is my integral. So the first segment gives me an integral where x ranges from 0 to h. E cosine omega t dx, because z is equal to 0 and cosine of minus omega t is cosine of plus omega t. 2 and 4 give me no contribution, so I go to segment 3. Now again j hat dot I hat is 0, so sine term will give no contribution. I hat dot I hat is 1. So along this path, z is equal to lambda over 2, so this is cosine k lambda over 2 minus omega t. So that's the integral. And x goes from h to 0. So I will have plus the integral x goes from h to 0, e cosine k z is equal to lambda over 2 on this segment, k lambda over 2 minus omega t dx. Okay, so if I perform this integration, there is nothing that depends on x here, so this integral will give me delta x, which is 0 to h, delta h, which is h. So this is going to give me EH cosine omega t. The second integral also doesn't have any x in it, so it will give me delta x, but now delta x, x goes from h to 0, so delta x will be minus h. So this is going to be E cosine, remember k wave number is 2 pi over lambda, multiplied with lambda over 2 minus omega t multiplied with minus h, because delta x is minus h. X goes from h to 0. So here I notice that these two lambdas will disappear, and the twos will disappear. So I will be left with the following: closed path integral E dot dl is equal to EH. Now, the first term here is cosine omega t. Here I have cosine pi minus omega t. What is cosine pi minus omega t? It is cosine pi cosine omega t plus sine pi sine omega t. And because of this minus sign here, I should write this as minus cosine pi cosine omega t minus sine pi sine omega t. And sine pi is 0. So this is 0. So that term doesn't contribute. On the other hand, cosine pi is equal to minus 1. So this is going to become cosine omega t plus cosine omega t. Therefore, I reach my final answer for part A. Closed path integral E dot dl is equal to 2EH cosine omega t. So that's the answer to part A of the problem. Let's move on to part B. What is the magnetic flux phi b through the loop P? Okay, so now we have to worry about the magnetic flux. So we can start by writing our magnetic field. Magnetic field as a function of z and t was given to us as B minus sine kz minus omega t I hat plus cosine kz minus omega t j hat. So this is our magnetic field. Now, how do we calculate flux? Magnetic flux phi b is equal to integral b dot dA. All right. Now, the question is, what is dA on this path? So, if I look at my direction of the closed path integration for electric field here, using the right hand rule, if I follow this path, my four fingers of the right hand curl in the clockwise direction, the thumb points into the page. So here I'm on the xz plane, so an area element on this plane is in the Cartesian coordinates is dx dz, and I take the vector to be in minus j hat direction. That's consistent with the path I have taken for the electric field. So this is going to be minus dx dz j hat, where I have used the right hand rule to be consistent with my path integral that I did in part A. So here x goes from 0 to h, x goes from 0 to h, and z goes from 0 to lambda over 2. So that is going to span the whole area. All right, so let's start with this integral. The magnetic flux phi b is a double integral. X goes from 0 to h, z goes from 0 to lambda over 2. And since the area vector is in minus j hat direction, I hat dot j hat is 0, j hat dot j hat is 1. So basically I will only have this cosine kz minus omega t term, and I have the minus sign here. So this is minus b cosine kz minus omega t dz dx. All right. So if I perform the x integration, I basically see that there's nothing that depends on x here. The x integration gives me delta x, which is just h. So this can turn into minus bh integral x, z goes from 0 to lambda over 2 cosine kz minus omega t dz. Now if I perform this integral, the integral of cosine kz minus omega t dz, so I already had a minus bh here. This will be divided by k, and then I will have a sine kz minus omega t, and that will be evaluated between z is equal to 0 and lambda over 2. So that's my task here. All right, so this is going to give me the magnetic flux phi b is equal to bh over k. K is 2 pi over lambda, or minus bh lambda over 2 pi. So I can write it as minus bh lambda over 2 pi. Then I have sine kz minus omega t. So k is 2 pi over lambda, 2 pi over lambda. I evaluate that z is equal to lambda over 2, so it's lambda over 2 minus omega t, minus, evaluated at z is equal to 0, I obtain sine of minus omega t. So that's my evaluation at z is equal to 0. All right. Now, I can rewrite this flux phi b is equal to minus bh lambda over 2 pi. So here I have the lambdas canceling and the 2's canceling, sine pi minus omega t. So that is sine pi cosine omega t minus cosine pi sine omega t. And sine of minus omega t is minus sine of omega t, so this becomes plus sine of omega t. Here sine pi is equal to 0, so this term will be 0. So I will be left with cosine pi is minus 1, so that's going to be minus sine omega t with the minus sign, plus sine omega t, plus sine omega t, 2 sine omega t. So I find the magnetic flux. This is going to give me a magnetic flux phi b is equal to minus bh lambda over pi sine omega t. Because I obtained 2 sine omega t, there's another 2 here. So this will be my final answer for the magnetic flux through loop P. Okay, So I have done two calculations here. One is the path integral E dot dl. Along this path dl1, I have z is equal to 0, y is equal to 0, x goes from 0 to h. E dot dl gives me a non-zero term here because j hat that I hat is 0, but I hat that I hat is 1. So the first term is integral x goes from 0 to h, e cosine kz, but z is 0, cosine of minus omega t, but cosine of minus omega t is equal to cosine of plus omega t, cosine is an even function, dx. The second path segment, where I have a change in the z value going in the k hat direction, I hat dot k hat, j hat dot k hat is 0. This gives me no contribution. The same thing happens on path 4, on the segment 4 here. K hat, the dot product with k hat is 0. For segment 3, I obtain the same integral as in the first segment, but now z is equal to lambda over 2 and x goes from h back to 0. So this is h back to 0 on segment 3. So let's note here that this is segment 1, this is segment 3. Okay, so performing this integration and writing for k 2 pi over lambda, and also using the trigonometric identity, cosine of a minus b is cosine a cosine b plus sine a sine b. I obtain the final answer for the closed path integral 2eh cosine omega t. As for the magnetic flux through this loop, if I consider this direction of the path that I have taken here, I can basically say that the area vector points in minus j hat direction with this convention. So the area element is dx dz on the xz plane, and it's in minus j hat direction. So I hat dot j hat is 0, so this term doesn't give any contribution to the flux calculation, but this gives a contribution. So b cosine kz minus omega t j hat dot j hat integral over dx dz. X goes from 0 to h, z goes from 0 to lambda over 2. This is going to define the full area here. And performing this integral and also using the sine a minus b is sine a cosine b minus cosine a sine b identity, I obtain the magnetic flux through the loop P as minus bh lambda over pi sine omega t. So here I want to note that this closed path integral E dot dl actually gives us the induced EMF. So we're going to use this in the next video when we discuss part